So in this video, I'm going to talk about deriving Fourier coefficients. So recall that we ended the last video by saying that we're going to try to approximate our function f of x in the following form. So as this sum of cosine and sine terms, and what we want to do is ultimately talk about how do we find these coefficients, the an and the bn. So I want to begin with a theorem that's going to help us. So the theorem says that the functions that appear here, like all these cosine terms and all these sine terms, they form an orthogonal set. So specifically, this first function is cosine of 0 pi x over L. And notice that this is just cosine of 0, which is 1. Okay, and then we also have cosine of pi x over L, cosine of 2 pi x over L, and so on. We also have all the sine terms, sine of pi x over L, sine of 2 pi x over L, and then it keeps on going. So this is an orthogonal set if we use the inner product, where the inner product of f and g is the integral from negative L to positive L of f of x times g of x. Okay, so one of the things that's going to help us show that these are orthogonal is using even and odd functions. So we've talked about these before, so I'm just going to briefly review these. So recall that for an odd function satisfies the formula that f of negative x equals negative f of x. So graphically, what that looks like is an odd function. It turns out an odd function always goes through the origin. And whatever it looks like on one side of the origin, graphically, this is symmetric about the origin. So whatever it looks like on one side of the origin, it's going to be the mirror image of that on the other side of the origin. So like the mirror image of this point through the origin would be down here. The mirror image of this point across the origin would be down here. So if we draw all those mirror images, it's going to look something like this. That's what an odd function would look like. An even function, on the other hand, is symmetric. So first off, actually, the formula is for an even function that g of negative x should be equal to g of x. And that's going to be symmetric about the y-axis. So when we draw a graph of an even function, they don't have to go through the origin necessarily, but whatever they look like on one side of the y-axis, they have to look like the mirror image of that across the y-axis this time, not across the origin. So whatever it looked like here, I draw the mirror image of that on the other side of the y-axis, not the origin. And if I draw all of that, I get something like this. Okay, so why these are useful to us in terms of integrals is, for an odd function, if you integrate it from negative L to positive L, so for example, let's say this is L, and let's say that negative L is over here. If I look at those, the area, so if I call this area A, the area from negative L to 0 would be negative A. It would be the opposite. So that means my whole integral is just 0, because those areas cancel each other out. For an even function, if we go from where L is to where negative L is, well, those areas would be both A. They're both the same. So they don't cancel each other out. Instead, what we can do is we can say, oh, this is 2 times the integral from 0 to L of g of x dx. So recognizing when we have even and odd functions in integrals that go from negative L to positive L can help us. All right, so let's get into the proof. So one thing that's going to help us prove that these sine and cosine functions are orthogonal is to say, well, are they even or are they odd? So we've seen before that sine functions like this are odd functions. They are symmetric about the origin. Cosine functions are even functions. So cosine functions specifically that look like this, they are even functions. Okay, so we're trying to show that our set of sines and cosines are orthogonal. So there are 3 cases that we need to consider. So case 1 is going to be, and it depends on whether we are taking the inner product of 2 sines or 2 cosines or 1 sine and 1 cosine. That's why we have 3 cases. So let's say that for the first case, we take the inner product of a sine function So let's go sine of n pi x over L with a cosine function. So let's go cosine of, and it doesn't necessarily have to be the same coefficient here, so I'll write m pi x over L. So the inner product of a sine function and a cosine function. So from our set, for all the sine terms, n has to sort of begin at 1. So n here has to be greater than or equal to 1. For cosine, what was the smallest the coefficient sort of got? That was 0 here. So for sine, the smallest it ever got was 1. It was technically a 1 here in front of the pi. All right, so I'm just going to erase that. Now let's bring it back. So let's scroll back down. So that means the coefficient of this m, the value of m, has to be greater than or equal to 0. So now let's write down what this inner product is. So this inner product is going to be an integral from negative L to positive L of these two functions multiplied. So sine of n pi x over L times cosine of m pi x over L dx. And now let's see if even and odd functions can help us. Because what we have here is, so the cosine is an odd, the sine function is an odd function, but it's multiplying this cosine term, which is an even function. And an odd function times an even function turns out to be an odd function. So it's not like multiplying integers, like an odd integer times an even integer is an even integer. It's not like that for functions. So I would encourage you guys at this point to think about why. So if it's unclear, definitely pause the video. Test it out. See if you can convince yourself why an odd function times an even function is going to be an odd function. And if you're stuck on how to show it, use these definitions, use these formulas for what an odd function and even function must satisfy. All right, so we are integrating an odd function from negative L to positive L. So the integral of an odd function, we saw this above, from negative L to positive L, that was just 0. So our integral here should just be 0. So that shows case 1 is true. If we take the inner product of a sine function and a cosine function, those are different things. In our set, that's 0. We just showed it 0. That means the sines and the cosines are orthogonal to each other. But we still have two other cases. So what if we take the inner product of two sine functions? And what if we take the inner product of two cosine functions? So let's do two sine functions next. So here is case 2. Now I'm going to take the inner product of two sine functions. And notice I've written m in one of them and n in the other, because the m and the n might be different. Okay, so the m and the n that go on the sine functions in our list, they have to be greater than or equal to 1. All right, so let's write out the inner product. It's going to be the integral from negative L to positive L of sine of m pi x over L times sine of n pi x over L. So the integral of our two functions multiplied from negative L to positive L. So we have a sine function times a different sine function. So there are a couple ways that we can go here. One is we can use the trig identity to help us simplify this. So I'm going to use what's called a product to sum identity. Product to sum formula or identity. And the formula is that if you take sine of an angle, alpha, times sine of another angle, beta, this will end up equaling 1/2 times sine of alpha minus beta plus so I think actually this should be a cosine. Sorry, this should be 1/2 cosine of alpha minus beta, and then plus 1/2 cosine of alpha plus beta. So is that right? No, I think this should be a minus 1/2. So minus 1/2. Okay, so I'm going to use this product to sum formula. Okay, so if we do that on our product of these two signs, what we get is, we get the integral from negative L to positive L. We'll get 1/2 cosine of m minus n pi x over L. And then minus 1/2 cosine, parentheses, m minus n pi x over L dx. So we get this. And I can't remember if I said this, but sorry, this should be m plus n here. I think I said m plus n. Maybe I just didn't write the plus sign. Okay, so that should have been m minus n in that first parentheses, m plus n in the second parentheses. Okay, so this can be one of two things. So if m and n are not equal, so if the m and the n are not equal, then it turns out that this will end up equaling 0. But if the m and the n are the same, this will end up equaling L. So I'm just going to give a sketch of the reason why. So if I were to look at this cosine term here, if m equals n, this becomes 1. And that's not counting the 1/2 that's in front of it. So the integral of this part will be non-zero. But if the m and n are not the same, the integral of this cosine term is going to be a sine term. But then when you evaluate the sine term at L and negative L, those will cancel out. And that has to do with the fact that on the interval from negative L to L, this cosine function sort of traverses like a full period. And when that happens with the periodic with something like a cosine function, the positive portions and the negative portions perfectly cancel out. All right, so we end up with these two situations. But the one that we care about most for our proof is the fact that if the m and the n are different, meaning if these are different functions, their inner product gave us 0. And that's verifying this orthogonality condition. So the third case is, what if we took the inner product of two cosine functions? So in that case, I'm going to skip the computation, but there ends up being 3 cases. So it's 0 if m and n are not the same. And that's going to verify the orthogonality for us, this first part. If m and n are equal, there's 2, sort of subcases. If they are equal and they're not 0, then this inner product becomes L. And if they are equal and they're both equal to 0, then the inner product ends up being 2L. So one other thing that I want to note about this is this integral that we worked out with the trig identity, we could also do integration by parts for this, but we'd have to do it twice. So there's another way to go about this integral without using that trig identity. Okay, so at this point we have verified the theorem. We've shown orthogonality in all 3 cases. All right, so now I want to talk about how do we find our coefficients, our Fourier coefficients. So let's suppose that f of x happens to be equal to its Fourier series, exactly. So I'm writing it's exactly equal to it. Okay, so what we're doing here, in a sense, is we are writing f as a linear combination of these cosine and sine functions, which we now know are orthogonal, as a linear combination of an orthogonal basis. And we saw this before in chapter 6 of linear algebra. So we are going to find the coefficients for a(n) and b(n) in the same way we did in chapter 6 when we were trying to write a function as a linear combination of an orthogonal basis. So let's find a(n) and b(n) by sort of utilizing the fact that we have this orthogonality, except now we're not going to use dot products, we're going to use inner products. So let's find a(n) and b(n) with inner products. So with inner products. All right. So what we will do specifically is, I'm going to take both sides of this equation, and let's take the inner product of both sides first with a cosine term like this, and then later we'll deal with the sine term. So let's start with the left-hand side, f of x. And let's take the inner product of f of x with a cosine term, with cosine of n pi x over L. Okay, and if we do that on the left-hand side to f of x, I need to do it on the right-hand side. So before I do it on the right-hand side, just notice that I need the n that's here to be greater than or equal to 0. Okay, so now let's take the inner product on the right-hand side. But on the right-hand side, we have a sum of a whole bunch of terms. So when we apply the distributivity, like when we do distribution with our inner product, what we'll end up getting is, we'll get a0 over 2, its inner product, with this cosine term, cosine of n pi x over L. And then we have to do it with all the cosine terms and all the sine terms. So now doing it with the cosine terms first. So the first cosine term in this sum is a1 cosine of pi x over L. So we take its inner product with this cosine of n pi x over L. And then I go to the next cosine term, which is a2 cosine of 2 pi x over L. And we take its inner product with this cosine of n pi x over L. And then we keep going like this. So dot, dot, dot. Eventually, k is going to be equal to n. And when it does equal to n, we'll get a sub n cosine of n pi x over L here. Same thing on the other side, we'll get cosine of n pi x over L. And then dot, dot, dot. So this keeps on going down. All right, so this case right here, this was when k equals n. Okay, but we still have to take the inner product of cosine with all the sine terms that we had here. All right, so we'll have, so plus, so the first sine term is b1 times sine of pi x over L, and then it's, so inner product that with the cosine term, cosine of n pi x over L, and then the next sine term is b2 times sine of 2 pi x over L, and take its inner product with the cosine term, so cosine of n pi x over L. Okay, and then dot, 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 so this would continue. So this would continue on down. So we've basically just taken the inner product on both sides of this equation with cosine of n pi x over L. And on the right-hand side, we did a massive distribution. Okay, so what I want to do now is I want to consider two cases. So the first case I want to consider is, what if n is 0? So if n is 0, in this formula, this cosine term, cosine of n pi x over L, will be cosine of 0. And that's just 1. So the left-hand side of this equation becomes the inner product of f of x with 1. And on the right-hand side, if you let n be 0, this cosine term is going to become 1. Okay, but we've shown in the previous theorem that, so technically I guess it's cosine of 0 pi x over L, and cosine of 0 pi x over L is 1. We showed in that previous theorem that cosine of 0 pi x over L would be orthogonal to everything else in the set. That means that this would be 0, and this would be 0, and this would be 0, and also with the sine terms would be 0, and the other sine terms would be 0. The only thing that wouldn't be 0 is this right here is 1, and when you take the inner product of that with a multiple of 1, because that's what a naught over 2 is, that is not necessarily going to be 0. So what survives is we have inner product of a naught over 2. And actually what I'll do is I'm going to factor out that a naught over 2. So let's factor out the a naught over 2, and then I'll be left with 1 in the first entry. And the second entry, the cosine term, is 1. All right. So that is super nice. That's why we wanted to take the inner product with the cosine term. It's because we have this orthogonality. That's why everything else canceled except for one of the terms. All right. So now let's go ahead and isolate. Let's go ahead and isolate for the a naught over 2. So if we do that, we get that a naught over 2 ends up being the inner product of f of x with 1 divided by the inner product of 1 with itself. Okay, so this gives us a formula for what a naught over 2 is. So I'm going to highlight this. This is a formula for a naught over 2. So in the text, you'll see a formula written in a slightly different way. If we simplify this, we get that a naught equals, if we multiply by 2, so we get a 2. And then if we evaluate each inner product, the top is the inner product from negative L to positive L of f of x times 1, which is just f of x. Okay, and on the denominator, we get the inner product from negative L to L of 1 times 1. All right, so what does this simplify to? So the denominator is going to be the integral from negative L to positive L of 1. If we evaluate this, this ends up being 2L. So then the 2's cancel on the top and the bottom. And what we will end up with is 1 over L times the integral from negative L to positive L of f of x dx. Technically, it's f of x times 1. And in the book, technically they sort of say like, oh, this 1 right here is cosine of 0 pi x over L. Okay, so I'm also going to highlight this formula because this is the one that sort of appears in the book. Okay, but I personally like this formula right here, this inner product one, because it shows how this Fourier series is connecting to inner products. All right, so now let's go ahead and figure out, well, what would our coefficient be if n was not 0? So if n was not 0, so I'm going to go ahead and go back to my work up here. I'm going to cross out all these, I'm going to erase all these crosses that I've drawn. So when n is not 0, then the only term that's going to survive is where the two functions that are being inner producted are the same. And that's this one. This one's going to survive. Everything else is going to become 0. Okay. Everything else is going to become 0 because these other sets of functions are all orthogonal. That's why their inner products are going to become 0. Okay, so what ends up surviving here, so I've just zoomed it out a little bit so I can see this better, is, so when n is not 0, on the left-hand side, we get the inner product of f of x with cosine of n pi x over L. That's what we get on the left-hand side. On the right-hand side, what survives is, let's factor out the an. So an factored out times the inner product of cosine of n pi x over L with itself, cosine of n pi x over L. So that's what survives on the right-hand side. So now let's zoom it back in. So solving for an now, if we isolate an is the inner product of f of x with cosine of n pi x over L divided by the inner product of cosine of n pi x over L with itself, cosine of n pi x over L. All right, so I'm going to highlight this. So this is a formula for an when n is not 0. In the textbook, they'll simplify this. They evaluate what each of the integrals is. So it turns out that this integral on the bottom ends up being L. That was one of the formulas in our piecewise function that we said in the proof of the theorem above. So I'll write that as 1 over L in front of the integral on top, which is from negative L to positive L of f of x times cosine of n pi x over L dx. So let's highlight this as well. So this is the formula that it says in the book when n is not 0 for what a sub n is. So if we compare this to the formula that we had for a0 for a naught, it has the exact same form, except in a naught, just notice that there's nothing with the f of x because it's technically cosine of 0 pi x over L. And that has the same formula that we got here for a sub n when n was not 0. And that's actually the reason why in the Fourier series, why we write a naught over 2 for this constant term. We write a naught over 2 for that constant term instead of just a naught, so that this formula for what a naught was matches up with the formula for what a n is when n is not 0. If in the Fourier series, if we didn't write a naught over 2, so if we didn't write a naught over 2, then this formula for a naught would have been off by a factor of 2. And that's because of a quirk in the integration that we saw above. Alrighty, so now let's just write down the formula for the sine terms. This one I'm not going to go through all the derivation. I'll just write down what the formula is. So similarly for the sine terms, the coefficient of the sine terms is b sub n. B sub n ends up being the inner product of f of x with the sine term divided by the inner product of the sine term with the sine term. And so I'm going to highlight this. So this is the formula that I usually prefer to use, this inner product formula. And in the textbook, they simplify that to this form. So the integral of f of x times sine, that's the thing on the numerator. The denominator, the inner product of sine with itself, that ends up being L. All right. So hopefully seeing these formulas where I have an inner product on the top and an inner product on the bottom might remind us of projections. And if you were thinking that at some point, awesome. If you weren't, that's okay. I know it's been a while since we've seen them, and we've gone through a lot of computation, and it's easy to get, kind of sucked into that. But I will, state that a little bit more explicitly just in a minute. So at this point, we already defined what a Fourier series is. So if f of x is a piecewise continuous function on the interval from negative L to positive L, we say that the Fourier series of the function f is this thing right here. So we write f of x, this squiggly line, we usually say is approximately equal to. So when I write this squiggly line, I'll mean that this is sort of the best approximation that we have to f of x using terms that look like this. So it's the formula that we saw before, where a sub n and b sub n, those coefficients are given by these integral formulas that we just derived. So these are the formulas that you'll see in the book. I'm also just going to more explicitly write down the formulas I usually choose to use, and those are those inner product ones. So this is the technical definition of a Fourier series. I think it's also helpful to see a more conceptual definition. So the conceptual definition is Fourier series. A Fourier series for a function f of x is an approximation of f of x using sines and cosines. Specifically, what it actually is it's a projection. That's what I was hinting at above. It's a projection of f onto the span of an orthogonal set of sines and cosines. So we're projecting f onto this orthogonal set of sines and cosines. Let me just say sines and cosines using inner products. And so under this framework, and we can see that that's, what's happening here. F of x, we're trying to write it as a linear combination of these cosine and sine functions. And we did that technically with projections. And that matches up with what we saw for the formulas for our coefficients. We wrote them in terms of these inner products, at least first, before I stated the book's definitions for what these simplify to. But this is helpful in terms of thinking about Fourier series and what they are more conceptually. So the next video, we will do an example where we actually derive these coefficients for a specific function.